Today I'm going to talk about Laplace transform and inverse Laplace transform. Of course, by the end, I will give you application in your field, electrical engineering. Let's go and see what's the point of studying Laplace transform. This is just a motivation to understand why we are studying Laplace transform. Of course, we know any mathematical modeling for electrical engineering is just a differential equation with initial value. This is why we call it initial value problem. Laplace transform will transfer the differential equation with the initial condition representing the circuit in your field or any other field, mathematical modeling with initial value as a differential equation, into algebraic equation, which is easy for you to solve the algebraic equation. Okay, and then you use a partial fraction. So you have to remember the partial fraction, math 1. And then you take Laplace transform solution. By using the inverse Laplace transform, you get the solution of the differential equation with the initial value. This is why you don't have constant in your solution. Okay, let's go first to know what is the Laplace transform. I would like to have the Laplace transform for the first derivative, and I would like to have Laplace transform for the second derivative, or the derivative in general, because I'm going to apply the Laplace transform into differential equation with initial value. Differential equation without initial value, you cannot apply Laplace transform, and we will see why we should have initial value, especially when t equal to 0. How to find the Laplace transform? The Laplace transform is the integration from 0 to infinity for what you are going to have Laplace transform for, multiply by the exponential function e to the minus st dt. S is a constant, t is a variable, so we are going to integrate with respect to t. Yes, I have a multiplication of two functions, so I'm going to use a partial integration by parts. What is the integration by parts? Let's go and remind you about it. So again, Laplace transform for any function f of t is exactly the integration from 0 to infinity for your function and multiply by e to the minus st dt. Okay, now s is a constant. S is a constant. Okay, so you integrate with respect to t all the time because you have a multiplication here. So you are going to use integration by parts. What is the integration by parts? I'm just reminding you that when you remember u dv is equal to uv minus the integration of v du. Okay, so you choose u, which is easy to differentiate, and dv easy to integrate, right? Okay, let's have an example before we go for the derivative. Find Laplace transform for section A, f of t equal to constant C. Section B, f of t equal to t. Section C, f of t equal to e to the at. Okay, and then we will go for dy by dx or f dash of x, and the last one e square y by, sorry, I should have t as independent variable. This is the default. Okay, or f dash of t. The last one, d square y by dt square or f double dash of t. Now let's go for the first one, f of t equal to constant. First of all, Laplace transform this is the knowledge you need for f of t as, yes, I write it like that, f of t equal to the integration from 0 to infinity for your function multiplied by e to the minus st dt. This is fixed in all Laplace transform because this is the formula. Now let's apply this one into section A. I would like to have Laplace transform for any constant c. So it will be integration from 0 to infinity for c e to the minus st dt. When you have a constant, you take the constant outside the integration, okay? Because the integration is a linear operator. E to the minus st dt, okay? Now, what is the integration of e to the minus st? Guys? Is it correct?
Yes.
Yes, the same exponential function over the derivative of the power, right? With respect to t, of course. And this is the boundary of the integration. If I substitute by the upper bound, so I have e to the minus infinity minus e to the 0 over minus s. All of us knows e to the 0 is what?
One.
You remember the exponential function exactly like that, okay? It is the exponential function. When x tends to infinity, it goes to infinity. At 0 is 1. At minus infinity is going to be 0. This is why the x-axis is horizontal asymptote for my function e to the x. Okay, so this is will be 0. So you end up with c e to the 0 is 1. So you have 1 minus 1 over minus s. So you end up with c 1 over s. Okay, fine. This is the first one. Let's go for the second one. B. I just remind you, we are going to find Laplace transform for the function f of t equal to t. Laplace for the function t equal to, yes, this is the formula of Laplace. I write the function and then multiply by e to the minus st and I integrate with respect to t from 0 to infinity. Yes, here I have my margin. I'm going to use integration by parts. Integration by parts. Okay. What is the integration by parts formula? Yes, I remember. When I have u dv, u as a function of x and v is a function of x, I can get u and integrate dv to have v minus v du. So in my case, which one I will take it u? I will let u as what? T or e to the minus st? Of course t, because when I have something to the power, the derivative reduce the power, right? So u equal to t, so du will equal to dt, and dv equal to e to the minus st dt, so v will equal to the integration of e to the minus st dt. So what is the integration of e to the minus st? Is e to the minus st over minus s. So this is all what I need. Okay, so here I'm just writing using integration by parts. Okay, and I have it in the margin. So Laplace of t will equal to uv, u as t, v as e to the minus st over minus s. And don't forget to write what? Yes, the boundary from 0 t equal to 0 to infinity, minus the integration of v du, so e to the minus st over minus s, du is dt, so here it is. Now I know e to the minus infinity will be what? 0, and e to the 0, when t equal to 0, t will be 0, and e to the 0 will be 1, so 0 times 1 is 0. So I end up with what? 0, right? So I have 0 here. Minus will be plus the integration of e to the minus st over s dt from 0 to infinity. Now the integration of e to 1 over s outside, because it is constant, from 0 to infinity for e to the minus st dt, which is, yes, 1 over s, and this is e to the minus st over minus s, from what? From 0, from t equal to 0 to infinity. At infinity it is 0, at 0 is 1, so I have 1 over s times 1 over s, so it will be what? 1 over s squared. 1 over s squared. This is the Laplace transform for t. Easy? Yes. If you know the integration, it will be easy for you. What is the next one? E to the at. See? Laplace transform for e to the at. Again, my Laplace transform is 0, from 0 to infinity for my function times what? E to the minus st, and I integrate with respect to t. Now I have the same base, so what you are going to do, you're just having the base and adding the power together. Now this is the integration from 0 to infinity e to the, I can take what? Common factor. I can take minus t as a common factor. So a, so this one will be s minus a dt. This is constant. So the integration will be what? Yes, e to the minus t s minus a divided by the derivative of the power, which is s minus a, and I have minus here, right? And don't forget, this is from t equal to 0 to infinity. I know e to the minus infinity, when I substitute by infinity, this one will be 0, right? When I substitute by 0, I have what? Yes, I have 0 minus, when I put the 0, so I have minus 1 over minus s minus a. This minus minus will end up with 1 over s minus a. This is the Laplace transform for e to the at. This is the Laplace transform for e to the at. Now let's go for the fourth one. I would like to have Laplace transform for y dash, okay, or f dash of t. It's up to you, okay. Let's use ly dash, which is Laplace for the first derivative dy by x. Again, I'm going to write the Laplace transform for this one will equal to what? Yes, equal to the integration from 0 to infinity for y dash multiplied by e to the minus st dt. Also, here I remind you how to integrate this one in the margin using the integration by parts. Integration by parts. Okay. What is the integration of by parts? I will remind you, u dv, uv minus v du. Which one I will take it u and which one I will take it v? Of course, dv, I will take it y dash dt. Why this? Because it is easy to integrate the integration of the first derivative is the original function, right? This is why I take this one. And what is u? U is the other part, which is e to the minus st. Du will equal to the same exponential function multiply by minus s, opposite to the integration. When you integrate, you divide it by the derivative of the power. Okay, let's do it. So Laplace transform for y dash will equal to, yes, what's u? U is e to the minus st. What is v? V is y. And don't forget, yes, you have to put from t equal to 0 into infinity minus v du. What is v? V is y. What is du? Yes, e to the minus st times minus s dt. Minus s is a constant, so I can take it outside. Before I will do this one, when I substitute by infinity, I will have minus infinity. E to the minus infinity is 0. Okay. And when I substitute by t equal to 0, e to the 0 is 1, but I still have y at t equal to 0 because y is a function of t. Okay. Now, This S is a constant. I take it as outside, and I have minus minus, so it will be plus. And I will have S outside. And what I got inside, I have y e to the minus st dt. What is this one? Yes, this is Laplace transform for y. This is Laplace transform for y multiplied by s, and I have here minus y 0. It's better to write it like that. Because I have minus here, it's better to write this one as s Laplace transform for y minus y of 0. This is why I'm telling you, when you use Laplace transform in the differential equation, you should know the initial condition at t equal to 0. I think you catch it now, right? So this is the Laplace transform for y dash. Let's go for Laplace transform for the second derivative. Laplace transform for d squared y by dt squared, or you can write it Laplace transform for y double dash if you like. Yes, it is exactly the same formula for Laplace transform. My function multiply by e to the minus st dt. Again, I have to remind you by using integration by parts. So what is your u? U dv equal to uv minus v du. In this case, my dv will be my second derivative dt. So v, the integration of the second derivative, is the first derivative. It's exactly like when you have the acceleration integration to give you the velocity. Okay, fine. This is v. Now, what is u? U will be e to the minus st. So you need the u, which is e to the minus st multiplied by minus s. Now, I have Laplace transform for y double dash will be, yes, uv. What's u? E to the minus st. What is v? Y dash. And don't forget you have from t equal to 0 to infinity minus the integration of v. What is v? Y dash. What is du? It is e to the minus st times minus s, and the integration with respect to t. This is why I can take the s outside here. So I have plus s integration from 0 to infinity for y dash e to the minus st dt. Here I know if I substitute by infinity, I have e to the minus infinity is 0 minus, when I substitute by 0, e to the 0 is 1, but I still have y dash at t equal to 0. Okay. Now, yes, what is this one? This is the Laplace transform for y dash. Okay. I have it already. Yes, I have it. Minus y dash at 0. Okay. Now I can copy it from here. Laplace transform for y double dash is SLY minus y at 0. So this one plus it is S, and I copy this one, which is S L Y minus y 0. Okay, minus y dash. That's it. Now I can arrange this one. Yes, so I can write this one as, because S times S is S squared. So Laplace for y double dash will equal to, I just write it in black, S squared Laplace of y minus yes y dash of 0, and remember this s also will be multiplied by, so minus s y at 0. This is the Laplace transform for the second derivative. Okay, of course not all the time you are going to do the integration. Okay, it takes too much time, right? Yeah, before I leave, if you have two functions and you would like to have Laplace transform for the addition, it is integration. This is why you can distribute the integration over the addition, and if you have a constant you can take it outside. So Laplace transform is behaving like definite integral, right? We got this one. Yes, this is why we don't want to spend our life computing all of these integral and having Laplace transform. So we have it in a table here. Okay, and also we have the formula for the n derivative in general. This is a special case for the first derivative and second derivative we already have done. This is a function when it multiplied by t, forget about the t and find the Laplace for f of t and differentiate it and change the sign. This is the first one. Okay, be careful, you have a Laplace and inverse Laplace. So if you get this result f minus f dash of s as a Laplace, you take the Laplace inverse for this one and you check it which one in the table and you get this one, right? And we will know how to find the Laplace inverse in details. Now this is, they call it S shifting theorem. S shifting theorem. When you multiply any function by the exponential function e to the at, forget about e to the at for a while, find the Laplace for f of t from your table and change s by s minus the coefficient here a, right? Okay. If you have f dash of s here, this is exactly repeated again. Okay. Now let's go for this one. How to do this one? So yes, Laplace for f of t will be 3 times Laplace of t plus Laplace for e to the minus 4t. What is the Laplace of t? I'll go for my table. Laplace for t is 1 over s squared. What is Laplace for e to the minus 4t? Laplace for e to the at, a is minus 4, so it will be 1 over s minus minus 4, it will be 1 over s plus 4. Yes, that's all. Okay. So this example just to check the linearity of Laplace transform. So it is behaving exactly like the integration. If you would like to integrate this one, You take the 3 outside, integrate t plus the integration of. Now you take in Laplace transform in the same way. What is the Matlab command for Laplace transform? Let's do this one, right? If you have Laplace Matlab, please try it with me. First, you define the two variable t and s, and then semicolon. The command for Laplace is Laplace and open bracket, write the function, comma. When you're having Laplace transform, you write comma t as input, comma s at the output. In the inverse Laplace, you just Laplace, I from the inverse, and here you just put s first and then t. Let's try it in the Matlab. Sims, I define the symbols. Sims s t semicolon Laplace open bracket. I have 3t, so 3 star t plus exponential function is written exp to the power minus 4 multiplied by t. I finish writing the function. I would like to have Laplace transform because I have a function of t, so I write t first, and I would like to have the function of s. Now, yes, he got for me the Laplace transform. Now, if I would like to have the Laplace inverse for this one, I will have the original function 3t plus e to the minus 4t? Let's do it. What you are going to do in Laplace transform in Matlab, Sims, also st semicolon. Instead of Laplace, you just add I from the inverse. So I Laplace open bracket. I will take this result as it is. Control C, Control V. A function of s. So I write s first, and then I need the output as a function of t. So I write t. Yes, if you would like to make pretty, to have the math for this one. Yes, it is the same function, 3t e to the minus 40. Okay, now I'll just get a screenshot for you, and I'll put it for you in the chat just to know how to find Laplace transform and inverse Laplace transform by Matlab. Okay, let's go further. We know how to find Laplace. Now we would like to get back. We get back using Matlab. We would like to get back by hand. How we can find the Laplace transform, Laplace inverse transform for this one? Let's do it by hand. I would like to have find inverse Laplace transform of f of s equal to 1 over s squared plus 8s plus 50. Of course, you will say, I will go back to the table Do I have this one or not? Do I have this one in the table or not? Do I have 1 over s squared plus 8s plus 15? I think I have something similar to this one if I have a I complete the square, or if I do the partial fraction. So it is better to do what is the point of doing the partial fraction? Yes, because I have 1 over s minus a has inverse Laplace e to the at. So I can manage with e to the at if I make a partial fraction. This is the point, okay, of using the partial fraction. So using partial fraction, I just remind you by the partial fraction. When you have 1 over s squared plus 8s plus 15, can you factorize this one? If you don't know how to factorize it, you can use your calculator, find the roots, and write s minus the first root times s minus the second root. Okay, but I know 15, I can write it as 5 times 3, and I have positive, so both practice will have positive. So I have here positive, and also I have positive in that aspect. And the 15 is 5 times 3, and I will have 8. This is a point. Okay. Now I did this one. The partial fraction start from here, right? Yes, I will have s plus 5, and I have s plus 3, because this is a first degree. The denominator is a first degree, so I will put the constant here, and then put the constant here. Okay. How to find this constant? You are lucky if you have a first degree. Okay. You just hide this one, right? To find a, hide this one here, right? So you hide s plus 5. What makes this one 0 is s equal to minus 5. When you're hiding this one and you substitute, you have 1 over minus 5 plus 3, so you have 1 over minus 2. So a will be 1 over minus 2. If you would like to have b, you just hiding what is down b, s plus 3, and you substitute s equal to minus 3, which make this one 0 in the other part. So you have 1 over minus 3 plus 5. Okay. It will be 1 over 2. So you find a and b in this easy way. Now I would like to have the Laplace inverse for 1 over s squared plus 8s plus 15. It is exactly equal to what? Equal to its factorization, 1 over s plus 5 times s plus 3, which is exactly equal to Laplace inverse for a, which is 1 over minus 2 over s plus 5 and plus 1 over 2 over s plus 3. Now this is constant, I can take it outside, right? So it is easy to take this one outside. So you will have minus half Laplace inverse for 1 over s plus 5 plus half Laplace inverse for 1 over s plus 3. I think I have seen this one before, and also it is in my table. Laplace transform having 1 over s minus a if the original function is e to the at. So you have to write it as s minus, right? So this plus, you can make it minus minus 5, right? And this one, make it minus minus 3. So a is minus 3 here, a is minus 5 over here. Okay? So what is that? Yes, is minus half e to the minus 5t plus e to the minus 3t over 2. This is the Laplace inverse. Let's try it by the Matlab. I just clear the window. I define the symbols since s e semicolon. What's my function? My command I Laplace, not Laplace, I Laplace. When I have f of s, I have to use Laplace inverse. Laplace is I Laplace. Open 1 over, yes, I have to open bracket for the denominator, s square plus 8 star s plus, finish writing my denominator, and comma, I input s, and I would like to have function of t transform. Okay, yes, let's make it pretty. Yes, it is exactly like what I have got by hand. E to the minus 5t over 2, e to the minus 3t over 2. Easy? Okay. I will stop recording now and I give you some example just to guarantee you can do it easily. And then we will continue solving the differential equation.